also start by saying I love this conference. It's a wonderful series. For those of you who are new to it, welcome. I hope you learn a lot. In recognition that people come here to learn a lot, in case there are a few hidden people in the audience who don't know what a hot Jupiter is, I put a system to scale right here, where you have a gas giant, several stellar radii away from its host star. We expect them to be tidally synchronized, so a very hot, constant day side and a cold night side, and weirdness. This is the title that I was given, but being in Oxford, I thought it needed an Oxford comma, both because that's how I roll, but also because in my mind, it makes more sense. I'll get to that in a little bit. And I'll get to that because if I'm saying that it's dynamic, comma, chemistry and clouds, I'm in a mindset that I have some dynamics going on. And then within that context, there's some chemistry and clouds going on. But really, I think it's more appropriate to have the Oxford comma because these three aspects of atmospheres are all interrelated and they influence both ways back and forth, right? So this is the context that we need to think about when we're thinking about what's going on in hot Jupiter atmospheres. Also, I have a strong three-dimensional bias. So I'm also going to point out they're all three-dimensional things we have to worry about. So we'll dig into some of these interdependencies. Before I get started, there's a lot of really exciting stuff going on in this set of topics. This is not a comprehensive literature review, so apologies. I've tried to smash a lot of material in here. I've probably forgotten your wonderful paper. I'm sorry. Please feel free to raise it as a comment in the questions afterwards, especially if you want to highlight work by more junior people. That's awesome. And thinking about junior people, I also want to say, come work on these topics. There's so much we don't know, right? Even as Adam was saying, for solar system modeling, there hasn't been necessarily as much as you would have thought. In hot Jupiters, we're really figuring stuff out. So at least in theory space, there's plenty of interesting problems to work on. Come work on all of them. I remember when I was junior looking at the leaders of the field and thinking, how could I ever possibly find a space when there's already all these people working on it? It expands. There's tons to work on, so come play with us. Okay, so in my abstract, I decided to be a little bit cheeky maybe, and I said, we don't really understand the basic picture of hot Jupiters. Maybe we do, maybe we don't. First, I'm going to kind of explain this standard picture that has developed. So this is the framework that many of us think of when we think of how hot Jupiter atmospheres operate. And I'll start by going back to some history and the original GCM. Oh, GCM. Thank you, Nick. I appreciate it. Before we put hot Jupiters in the titles of papers, and so this is, I think, the first GCM of a hot Jupiter. And I noticed when I looked back at that, even in the abstract, Tristan and Adam were very smart to point out, okay, first of all, huge day-night differences, very strong wind speeds. And then I noticed substantial departures from chemical equilibrium are expected. The cloud coverage depends sensitively on the dynamics, right? Cool, it's already all been done. Chemistry, dynamics, and clouds right from the beginning. There's been some work to figure things out in the meantime, but here's the basic result, right? And this hasn't changed very much. Here's something like temperature as a function of latitude and longitude on the planet, and the winds are showing, or the arrows are showing you winds. And so there's this classic standard picture where we developed this eastward jet along the equator, and it takes the gas that's at the central point, the substellar point facing the star, and it vects it downstream a little bit before it has a chance to cool efficiently. And so you have this temperature pattern that's got this standard shift of a hot spot. Nicely, this also matched early observations of longitudinal structure around the planet. So here's a classic first continuous orbital phase curve of thermal emission from the hot Jupiter. And here's kind of the phase of the planet that we see as we observe the flux from the system as a function of time. So here's transit, the night side faces us, and then it turns around and the day side faces us, and it goes into eclipse behind the star. So at this point, you're just seeing stellar flux. If you zoom in, here's all the flux from the planet, right? And you see it's less flux here and more flux here. And in fact, the peak happens a bit before the secondary eclipse. And so if you translate flux versus orbital phase to flux on different longitudes of the planet, you have that the brightest region of the planet is a little bit east of the substellar point. Yes, this is what we expect. This works really well. And then there were more phase curves. So here's another one, and it peaks maybe around the substellar point. That's fine, because, right, the picture is that you're moving this hot gas away from the substellar point. So maybe you just have a shorter radius time scale and it's cooling more efficiently. You can still have this eastward flow. It just can't move the hot gas as efficiently. Nick provides a weird phase curve. Well done, Nick. This was a weird system, so let's ignore it. Here's another phase curve. It looks like it peaks maybe around the substellar point. Here we go, peaking before, peaking around, peaking around, peaking before. Cool, right? So things kind of make sense. We're happy with this picture that we've painted for ourselves about how hot Jupiter atmospheres and specifically their dynamics work. And we have a bunch more models. So this is kind of representative of different work by different groups. And we all plot things differently, but we mostly have similar answers where you get this eastward advection. And so our data, our models, they generally all agree. And Showman and Polvani even identified this nice physical mechanism that results in this eastward jet at the equator. Wonderful. Until we look a little bit more closely. So this is a plot from a nice recent, oh, I'm sorry, I missed your eye. Apologies. From a nice recent review by Vivian and Ian Crossfield. And it's showing this hot spot offset as a function of equilibrium temperature for a bunch of different planets observed at a bunch of different wavelengths. And you see here's lots of eastward shifts. Positive values are eastward shifts. Cool. Here's, this is your troublesome data point again, yeah, okay. Nick's to blame again for this. But we have these eastward shifts, okay. But the problem is there's also this curve from one of Vivian's GCMs showing a prediction for what the hotspot shift should actually be for a bunch of equilibrium temperatures. And it's rather off, right? And you may have noticed I bolded that this GCM has chemical equilibrium, is cloudless, and drag-free. I'll explain that in a minute, right? But this is kind of our vanilla standard picture, hot Jupiter, and it doesn't work very well. And I'm even going to point out it really doesn't work well for some planets. This one is a planet that I love. It's unfortunately non-transiting. And so we have less information about it and has had less observations. But this planet in its phase curve has this huge offset. Basically, the hottest point's around at the terminator. And a point that's missing from this is some nice work by Lisa Deng with a planet that has a westward shift. And I should mention, these are all thermal emission, right? So you might be thinking, oh, westward shifts in Kepler phase curves, that's different. I'll get to that in a second. But these are all thermal emissions, right? And so not only does this form of points just seem maybe a bit lower, but we're observing kind of even more weirdness going on with this planet. We can also not just look at the phase curve offset, but the difference in flux between the day side and the night side. because these things are related, right? If you can move the hot spot around fairly well, you can probably also minimize day-night differences. And so again, here's the vanilla prediction, and it doesn't really work, right? 1 means a very large difference between the day side and the night side. Okay, so we have this beautiful standard picture of hot Jupiter, and I don't think it's completely wrong, but I think that we don't quite have things as sewn up as maybe some people perceive. And by people, I mean the people who say, why does anybody study hot Jupiters anymore? Don't you already know what's going on? No, there's more to learn. It's not within my title slide of physical things to talk about. I'm not going to spend time talking about what if planets aren't in synchronous rotation rates that can affect what's going on with circulation. And I'm also going to not talk about what if their rotation axis has some non-zero obliquity. But these are also other things that can make circulation weird if we don't understand what's going on. Okay, so even though I made this point at the beginning that this is the wrong way to think about it, I'm going to start by ignoring chemistry and clouds for a second and just thinking about dynamics, right? So within this context, where so far I've been ignoring chemistry and clouds for this standard picture of hot Jupiters, within this context, what else could be going on just with the dynamics that doesn't quite make sense? Well, here we come back to that drag-free that was in the vanilla version of the hot Jupiters. Here's those same plots again, but now in these GCMs, this time from TAD, there's been this drag time scale. So there's something slowing down the winds on some time scale, and you can play with that value. And these lines maybe match the data a little bit better, and they're implying that the circulation is not as efficient as we might think, right? There's something that's preventing transport of heat around the planet and keeping these values closer to 1, keeping a larger day-night difference, right? And similarly, preventing the hot spot from moving as far away from the substellar point. And this drag is a proxy for the very unfortunate, complicating fact that these planets' magnetic effects might matter, and in really gross, disgusting, horrible to model ways. So before, we heard about magnetic effects mattering very deep in Jupiter, right, and slowing winds down there. This is a different context, but similar idea, right? The reason it's a very different context is that you're not moving to a region that's increasingly homogenized and where you're getting metallic hydrogen. Here, your ionization is coming from the fact that the atmosphere is so hot that you're starting to kick off electrons. You've got thermal ionization going on. So you have these charges embedded in winds that are blowing around the planet. The planet has a magnetic field. I hear tell charges don't like to move through a magnetic field. And so there's a back reaction on the winds that acts to slow them down. But even though we did some timescale estimates long ago, it's not a drag timescale, right? And these are actually plots of estimates of some magnetic timescale at a couple different locations in the atmosphere. And this is the log of the timescale. So between the day side, where you have very short timescales, it's really hot, ionization should matter a lot, and the night side, where you have basically infinite timescales, it's messy, and it changes at different depths in the atmosphere. It's inherently three-dimensional. It's just disgusting. It's really gross. There are a few brave souls working on doing what's inherently non-ideal MHD to model these atmospheres correctly, and we should fund them more. A recent example of MHD modeling of hot Jupiter atmospheres is this work, which I think is actually a shallow model, so it's very hard to do it all right. But here's the flow pattern you get without any magnetic effects they turn on some magnetic effects, that's what this thing means, and instead they've disrupted the circulation pattern and it's westward. Now, in this work, from these kind of scaling estimates, they said, cool, but that weird planet that I pointed out before with the westward shift, you would need like 3 kilogauss to produce this according to their scaling. So problem far from solved. Here's where I started to reach the point that I realized I had too much to talk about, and so I must apologize for some bullet point lists of things. But aside from this gross magnetic stuff, if you move to the cooler hot Jupiters, where magnetic effects shouldn't matter, you can still worry about whether we're getting the standard picture correct in terms of dynamics. There's been recent work looking at actually what's the dynamical mechanism that we have in our standard picture, thinking more about subgrid physics, our transonic flows. Shocks may matter, but maybe not that much, actually, it turns out, surprisingly, maybe. And also thinking about depth of jets and directions of circulation. So can't talk about them, but go look at them. However, I'm also going to highlight a couple more papers that specifically are thinking about, within this context of the hot Jupiter dynamics, what are the implications for how things are mixed around? Because this is moving us more in the direction of what's going on with the chemistry in clouds, right? And so thinking about dynamics, how we're thinking about it, how to assess what the mixing between different regions is, because as most of the rest of the talk will talk about, I will talk about, this matters a lot for the chemistry and clouds. So getting into the chemistry now, we've moved back to this context where all the things matter. I will also admit I'm not going to talk as much about the connection between chemistry and clouds because I have this three-dimensional bias. But on a local scale, of course, your chemistry and your clouds inform each other, what exists, what can form. If something rains out because a cloud formed, then that also changes your chemistry. So that's as much as I'm going to say about that arrow. But let's talk about this a bit more. So again, it's been recognized for quite a while that dynamics can, and actually probably should, bring things out of local chemical equilibrium, which is to say that if you take a temperature field for a planet and based on the local temperature and pressure conditions, try to figure out what should exist there, then as we learned from Yamila, we have methane where it's cold and we have carbon monoxide where it's hot. The problem is that if you add just something very simple in your model to let there be a conversion between these two with the dynamics, then it looks like there's an asymmetry, but actually just look at the scale here, you get carbon monoxide everywhere in this model. Similarly, you can have vertical mixing. So this is an example as a function of pressure of the amount of methane on a hot Jupiter's day side. So taking the temperature profile on the day side. And if you have equilibrium, you get this blue curve right here, right? It drops off. We just said that. You should have carbon monoxide instead on the day side. But if you allow there to be vertical mixing, you can have this quenching effect where you, in fact, maintain a lot of methane. Oops, forgot about the photons. Photochemistry matters too. It's tricky. More recently, people are continuing to revisit this and try to do it in a little bit more detail, kind of tracing chemical conversions with the dynamics. So here's an example of 4 different major species looking as a function of pressure, how much there is. And these blobs of lines are actually for different regions around the planet. So you can see high in the atmosphere, quite a lot of variation around the planet, and it gets less variation as homogenized deeper down. And the 4 different plots are 4 different assumptions about whether the planet has a stratosphere or not, and what the carbon to oxygen ratio is. And so all of these then influence what's going on in terms of the chemistry. It's also worth noting that we need to be really careful about calculating chemical equilibrium Actually, chemistry is hard. Last time I took it was in high school, but it's tricky. It's tricky. It's complicated. And so people are also working to try to improve how we're modeling the chemistry in these atmospheres, which is very important if we want to talk about equilibrium or disequilibrium or just what species to expect. Also, if the chemistry is not equilibrium, then the opacities throughout the atmosphere change, right? It's these species that are providing opacity. So if you change what exists where, that means it changes how far into the atmosphere you see. So this is a lovely example of that. Results from a three-dimensional model showing as a function of pressure and now longitude around the planet, the contribution function. So where it's very dark, that's mainly the region that we're seeing. I think, 8 micron Spitzer band, right? And then these are lines of temperature on top. So if you compare a model that assumes chemical equilibrium to one that uses a scheme to let the chemistry come out of equilibrium, you may notice the temperature lines, the numbers are a little bit different. The pattern doesn't look that different, but the contribution function now is different, right? There's kind of this up, down, slide up again, whereas this is just kind of this wave, right? So changing the chemistry changes what part of the atmosphere we're seeing in our observations. And so maybe how we interpret them too. Because these opacities are changing, that also means that the actual physical heating of the atmosphere is changing. And it's differential heating that drives dynamics. And so if you're changing in a spatially inhomogeneous way how you're heating the atmosphere, this has consequences on your dynamics. So for example, here's some more recent work saying, let's just assume something about the chemistry and therefore opacities in the atmosphere. Maybe it's mostly carbon monoxide or mostly methane. And these are delta temperatures at a couple different heights in the atmosphere between, I think this is between a chemical equilibrium model and these two different models. And so you end up resulting in different temperature structures because you've changed how you heat the atmosphere because of chemical disequilibrium. In an extreme example, for these ultra hot Jupiters, they're terrifying, not just because they're magnetic, but also because on the day side, it's hot enough that you actually should probably dissociate your molecular hydrogen into atomic hydrogen. This is a huge change in the most abundant molecule in the atmosphere. And this can have important consequences from an energetics perspective, a dynamics perspective. And so this, I think, was a research note, Ted, yes, somewhere, kind of trying to put some initial effect from this dissociation and the heat associated with the dissociation recombination, and looking again at this day-night contrast as a function of equilibrium temperature. And so these different colors are, without drag or with drag, because we think things don't work how we think they should. And now the dotted lines are the original ones where you don't have any dissociation, and the solid lines are trying to include some proxy for that dissociation in what's going on. So ultra hot Jupiters, I know observers love them because they're so bright and wonderful. They're terrifying from a theory perspective. Okay, so clouds. You notice I put and or hazes because I have been well taught to think about aerosols, which I'm sure Sarah will do her soapbox for us again. But they could be clouds or hazes, and in many cases we don't actually know. My title said clouds, and more people have been focusing on clouds because they're maybe easier. I don't know. But we'll hear more about hazes from Sarah. And then, of course, I want to recognize we have a whole session about clouds later, and we're even going to hear some more about hot Jupiter clouds again later. But within here, let's really focus again on how this interacts in a three-dimensional sense with the dynamics. Okay, so observational evidence for aerosols usually means showing David Singh's lovely plot with all the different hot Jupiter spectra, and that's true. In a 3D sense, I'm instead going to show one of the first examples of invoking clouds. I've noticed it's very on trend to invoke clouds if you don't know what's going on with your observation. So this is WASP 43. I showed this phase curve earlier with the whole plethora of other ones, but if you notice a little bit more carefully, the flux from when the night side of the planet is facing us is basically the same as during secondary eclipse, which means you're just seeing the star, which means you're not getting emission from the night side, right? And I'm picking on this planet, but this is a general theme that we looked at before in the population of planets, that there's a very large difference in flux between the day and night side for many planets. And so you can say, just put some clouds on the cold night side, and then it's dim, and it works, right? Maybe. I also really like this data set, which is Kepler. So this is reflected light. And here, the phase curve happens, the peak of the phase curve happens after secondary eclipse, which means the brightest reflected region is west of the substellar point. Okay, so if we think about our standard picture of hot Jupiters, right, we have this eastward jet going around the equator, and a hot day side, a cooler night side. And so if you bring some of this hot gas around onto the night side, it cools, forms clouds, but you still have this eastward motion. And so it's going to bring some of those clouds around to the day side, and then they'll dissipate, but you might have some clouds hanging out on the western side of the planet, causing some enhanced reflection. See, this standard picture of hot Jupiters is really nice. I just think it's not fully complete yet, but it kind of makes sense. It's not ridiculous to say that this might be what's going on. Okay, so dynamics controls where clouds form, right? You need the right conditions for clouds to form, but that's not enough. This is a beautiful cross-section from one of Vivian's papers. This time I included the I know how to spell your name. And this is showing the temperature throughout a three-dimensional model. And here it's being sliced along the terminator, the day-night boundary. This is the North Pole, the South Pole. This is the east side and the west side. And this side's hotter. So I guess the substellar point is facing us. Yes, okay. So you can see here's the hot gas that's blowing to the night side from the day side. And here's cooler gas that's coming from the cold night side towards us, if we're looking at the day side. And on top of this are plotted condensation curves for a few different species. Notice it's mineral and metallic dust that forms clouds on hot Jupiters. And I like this way of showing the condensation curves because it's showing that clouds are a regional effect, right? Very spatially inhomogeneous. And also, for clouds to exist, you need to take the material that has these species and you need to pull it across the condensation curve so that it can form a cloud, right? I don't do clouds, so that's my simple understanding of it. So there are people who do clouds and are trying to do a more complex version of it. And so within this context where you have very spatially inhomogeneous conditions, you can take kind of profiles at different regions around the planet, and you can say, let's think about the time scales as a function of pressure, right? For material growing, nucleating, sinking. Let's also think about what's going on in terms of both the horizontal and vertical mixing that's helping this stuff grow or not and move. And you can kind of do these more detailed calculations using cloud microphysics to try to figure out what's actually going on. And you can get things like the distribution of a couple different kinds of clouds as a function of the particle radius at a couple different pressures. And it's wonderful. Thank you for doing these calculations, but it's complicated, right? You have these really weird distribution of particle radii. It depends on your pressure. This is at one location, right? It's very complicated. And it's very complicated in part because you have these really complex structures, because you have this day-night forcing and the responding dynamics. Also, the clouds don't just exist because of the dynamics. The clouds then also feed back onto the dynamics, right? So here's very pretty plots showing within a 3D model that Michael Roman did what the distribution of some of these different species look like, and then what the total cloud reflection on the day side is, right? And one thing to notice is that, first of all, of course, different species exist in different locations, but especially with whatever this thing is called, this species, there's this patchiness on the day side. And there's this patchiness on the day side because there's this radiative feedback that exists, where when you form a cloud, now it becomes more reflective and can have some absorption properties too. So it's changing the light that's coming in to warm the planet in the first place, as well as the ability of the planet to emit thermal radiation. And so this changes the temperature structure, and so then the clouds may dissipate, right? So it works both ways. You form the clouds, and then also the clouds inform the dynamics and the 3D structure. This is another example of a 3D model with some clouds included that have feedback onto the circulation, and it's wonderful and terrifying. And I say that because here's a plot showing the flux from the planet. So here's our eastward shift. Isn't it beautiful? It's a little patchier than we're used to, but still in this nice eastward shift. Here's the clouds that exist in the atmosphere. And then 24 hours on this planet later, here's what the flux looks like. And it's different, right? Some significant variability because you have these clouds. Sorry. Okay, so I think I have a little bit of time left. So I'm going to try, recognizing that I'm biased towards theory, and so most of those papers were very theoretical, how can observations help us try to understand more, right? We had some observations that led us to think that maybe our standard picture of hot Jupiter needs some revision. How can we do a bit better? And of course, the requisite answers are space missions and extremely large telescopes. And there's kind of some obvious consequences from this, which were also mentioned. Sarah kept calling out the need for spectroscopy instead of photometry. Spectroscopy is great, right? And spectroscopy at the longer wavelengths that we're going to get from these missions is going to inform us of what's going on with some of the species that we're really curious about, right? It may also help inform what's going on with some of the clouds, if we can actually start to see some features from cloud particles. So spectroscopy in general is just fantastic for better understanding what's going on with an atmosphere, especially at some of the longer wavelengths that we're going to get from these space missions. HRS stands for high resolution spectroscopy. And if you've looked at the program, you know that Jane's going to give us a whole talk about this. And so I have refrained myself from calling out how wonderful this is going to be to understand atmospheres in better detail. But this is one of my favorite things going on observationally right now. It gets you exquisite information. It's spectroscopy, as is in the name. And it also is letting you probe very detailed information about the atmosphere, and including sometimes something about the atmospheric dynamics. So, as I said, it's one of my favorite observational methods right now. But I'll just call out two more things. One is variability, right? So a standard assumption, part of the vanilla picture of hot Jupiters, is that it's a relatively steady state, right? You have these very strong spatial asymmetries, but when we run our nice standard GCMs, they don't change that much, right? And that's convenient in many ways, but some of these other effects that we need to worry about could potentially induce some variability, right? We just saw that example from clouds with feedback on the temperature structure. The horribly gross magnetic effects can also perhaps induce some variability. So here's a couple recent observational papers trying to constrain or detect possible variability in hot Jupiter atmospheres. And if they are variable or not, that's informative. And if we can characterize how much or not they are variable, that can help limit some of our models trying to understand the physical processes at work. And then, because it's my other favorite observational technique, and I don't think I can give a talk at ExoClimes without talking about it, I love eclipse mapping. So this is a technique where as the planet goes behind the star, you measure the shape of the secondary eclipse very carefully. And these changes in flux are related to the brightness of a slice that you just covered or uncovered. And so you can use it to make a 2D picture of the planet. And that's cool, right? So from phase curves, we get information longitudinally around the planet. But with eclipse maps, we get 2D information, latitude and longitude on the day side. And I think it's an especially exciting time for eclipse mapping because when JWST launches and people do a bunch of secondary eclipse spectral observations of a bunch of bright targets, many of those data we think should be good enough to actually make maps. And most people who are doing these JWST observations are going to be doing them spectrally, right? And so that gives us the opportunity to make multi-wavelength or three-dimensional maps because we see different depths at different wavelengths. Whew, just gets me so excited. So there's a group of us, and I say us in the loosest sense, I'm just along for the ride, who are trying to develop this technique that combines some spatial mapping optimization with spectral information as well. So, come talk to any of the names on this slide if you want more detailed information, but this is an example of this technique where you input this cartoon map with this very artificial hemispheric difference and different spectra in those hemispheres. And this is the output. So you group into a brighter region and a dimmer region. And you also have spectra associated with each of these regions, which look pretty good compared to the original input. So super exciting. Stay tuned. And with that, I think I'm about out of time. So this is it. This is my takeaway point. When you're thinking about hot Jupiter atmospheres, they're inherently three-dimensional, and the dynamics, the chemistry, and the clouds, or hazes, are all interrelated in a way that we can't really ignore without missing something potentially first order about what's going on in the atmosphere. Thank you.
Thanks so much, Emily. That was fantastic. I got my eye at the end. I'm happy. So we're going to take, we have some time for questions, and so we want questions from everybody. Don't hesitate to raise your hand. And don't forget to state your name or affiliation before you talk. So Christian?
Christiane Heddings and Andrews. Thank you so much for this entertaining talk. It was very enjoyable. First of all, I would like to follow your call for advertising young people's work. So there's a beautiful poster by Dominic Samra out there in Head P7B, which we did with a whole group of young people. So have a look, and there's beautiful detailed cloud formation modeling on this poster. Second point, if you want to make, you say that clouds are determined by the dynamics of the atmosphere. I would like to go a little bit deeper and say they are determined by the thermodynamics, right? It's not the hydrodynamics. The hydrodynamics sets the stage, basically. But what determines the cloud formation itself is the local thermodynamic conditions, which are then determined by the dynamics.
Agreed, fully.
Nick? So do state your name and affiliation, please.
Nick Cowan, McGill University. So I have a comment and a question. My comment is that weird phase curve of WAS 12 was not my fault. So my student Taylor Bell just put a paper on arXiv, and that shit is real. Yeah, like it's seen independently at different epochs by like 4 different groups who've tried analyzing it. So it's real, and we think it's actually gas falling, like the planet is getting eaten by the star. Okay, so my question is about the Roman and Rauscher paper or the Lyons paper. Has anyone, so those were people trying to be self-consistent. Those are theorists pretending that like they understand physics. Have any theorists for fun tried to look at the Demery albedo map of Kepler 7b, which inconveniently was not actually made into an albedo map, was some sort of like flux map or something. But in a review article, I once converted it into an albedo map for fun, and I was like, whoa, this is crazy. Like the Western Hemisphere is like 60% albedo, and the Eastern Hemisphere is consistent with 0. So have any theorists tried plugging that into a GCM and see whether you can actually maintain eastward flows under those circumstances? Because like naively, I would think you might start getting, like it would just screw up your dynamics altogether.
Right. If you have one side of the planet that is extremely reflective and the other that absorbs no problem, and by extremely reflective, like 70% reflection. Yeah. So in Roman and Rauscher 2017, we did that exact test. And people found that actually you still maintained the standard eastward circulation. Yeah. Yeah. Thanks for setting that one up. That was nice.
Hi, Shamila Miguel from Leiden. So I have a question. I know that I have a biased view towards solar system planets, at least on this. But I want to know how important are the lower boundary conditions. Like, I never know how deep you go in your modeling when you are doing this 3D, and how important it is to go even deeper on this.
I love it because it's a question that I can geek out about that most people don't care so much about. Although, okay, I have like 3 different things to say, and they're all fighting to get out of my mouth. So first of all, we generally put bottom boundaries at like 100 bar. And this is important to make sure that it's deep enough, because the atmosphere that's being actively heated, where the circulation is all happening, needs to have momentum exchange with the deeper kind of inert layers. If you put the boundary too shallow, then you're constraining all your angular momentum exchange to be within this thin layer, and then you can trigger instabilities that don't actually, we think, exist. It's also put... but then the choice for how deep to put it is also informed by many of us wanting it to be above the radiative convective boundary so that we're still in a stably stratified zone. Turns out there's been this series of wonderful papers recently, including one by Thorngren et al., that's pointing out that we know, which I didn't talk about, many hot Jupiters are inflated, right? Larger than we think they should be, some extra heat source in the interior. This implies a hotter interior than compared to Jupiter, for example. And so your adiabat actually is misrepresented if you're using a Jupiter-esque adiabat. And so maybe your radiative convective boundary is actually at much lower pressure than is part of this image people have had in their mind for a long time. And that has many, many interesting consequences.
Felix Sainsbury Martinez, CA Parasaclo. So with the eclipse mapping you're looking at, do you have any plans to look at the Rossiter-McLaughlin effect and maybe try and analyze the winds and see if you can get measurement? Because if you've got the spectral data, you should be able to look there.
So I think there's a poster about that, Nick.
Yeah, my student Melissa Marquette has a poster about that.
Okay. Will do.
Melissa Marquette poster. Go see it.
Sorry, so Daniel Call from MIT. Very naive question, but how many eclipse maps do we actually have? Why don't we have more? Ultra-hot Jupiters should be probably a very good target for this, but would we learn anything by doing eclipse mapping from them?
One, there's one planet that, to my knowledge, has eclipse mapping quality data, and that's HG1A9733b, which when non-scientists think they're being funny and ask me what my favorite planet is, that's my favorite planet. And it's a bunch of stacked together 8-micron Spitzer data. So that's part of the reason that we don't have any other maps is there are no more 8-micron Spitzer data. And you need to have precise measurements in a short enough exposure that you can trace out the ingress and egress well enough. Ultra hot Jupiters, I agree, would be really interesting to do some signal to noise estimates to see if that's going to produce something interesting. And I think, yes, it would be really informative because, as I pointed out, if you can do it spectrally, then you're not just getting kind of a map of thermal emission, which in itself is cool, but maybe in the standard eastward picture is not that different from the information you get from phase curves. You see an eastward shift. But if you can do this spectrally as well, then you would learn things about, for hot Jupiters, right? Maybe you learn something about whether molecules coming from the night side can exist on the day side for a while before they're dissociated, because you would see spectral features associated with different spatial locations on the planet. For things like clouds, right? It would be really nice to know if in a map with a bright region and a dim region, is the dim region look like a spectrum of a cool location, or does it look like a spectrum of a cloudy location? Because both are ways to make it dim, right?
Denis Sergeyev from University of Exeter. Is stellar variability included in this model, and are such things as solar flares important for these models, and have there been any studies?
I try to ignore the star as a thing other than an flux input into the model. Yes, the star is supremely important in all the ways. So it's important both in terms of interpreting the observations. You want to make sure that the variability, spatial or temporal, that you're measuring from the planet is from the planet. As an input into the models, it depends on what type of model you're thinking about. It's very important for modeling the upper atmosphere, which I haven't been talking about as much here. I'm talking about deeper pressure layers, but upper in the atmosphere where you're having evaporation, where you're absorbing your UV flux more strongly, it can have very important consequences up there. It's the short answer.
Yeah, Elena here.
Elena Monjavacas, Keck Observatory. So talking about variability, I would like to make a comment about what you commented of hot Jupiter variability. So hot Jupiter and brown dwarfs are not such a different type of objects. They are different, but not that much. In brown dwarfs, we have found so far variability up to some extent in all of them, basically. So I just wanted to let you know that we anticipate also that hot Jupiters are most probably also variable. So,
yeah, I love brown dwarf science. I think it's fantastic, and I think the variability from brown dwarfs is amazing. There are certainly important atmospheric similarities. A difference is the spatial pattern that we expect for inhomogeneity. So the brown dwarfs, right, are maybe having kind of more bands, more spots, and a different spatial distribution of why they're variable than we might expect for the hot Jupiters. So I expect that we will see different types of variability if we do start to see more variability on hot Jupiters.
Two more questions from the back, and then
Joe Harrington from the University of Central Florida. Just sort of a step back question. How far are we today from a model that has dynamics, active chemistry, radiation, and clouds, including the latent heat from chemical reactions? Because we know that in our atmosphere, the latent heat from condensation is a major effect.
Yeah, I don't have one in the works. Does anybody in the room want to? Nathan.
Yeah, we have that. the blocks that Emily was saying include dynamics, microphysical clouds, and then radiation feedback as well.
Hi, Matej Malik, University of Maryland. I have a related question, actually. So I'm working on radiative transfer myself, and you didn't really mention how you treat the radiative transfer in the dynamics models. And I know that this is a very difficult issue, also computationally wise. So I guess, do you think there is still a lot of work to be done in terms of increasing the accuracy of radiative transfer treatment? And also, what would be the impact? I mean, it's all coupled, right? So you will have the different heating, you will have different temperatures, different condensation points, and so on, which means the clouds are shifted. Maybe they don't form at all. So can you comment a little bit more on that?
Yeah. As you say, the radiative transfer is very important, right? That's how you're driving the dynamics in the first place, and also how you're observing the planet. So it's very important. I think that, of course, there's room for improvement, but I think it's important. It's important to think about the level of complexity that one is modeling at and the physics that you're going after, right? So I think when you're doing these wonderfully complicated GCMs with all the chemistry and all the clouds, you really need to make sure you're getting your rate of transfer correct at the appropriate level of complexity for everything else that's going on, right? Each of these pieces should basically be of comparable complexity, because if you're doing this wonderfully beautiful, detailed cloud microphysics, but doing some slapdash simple radiative transfer, I don't know how that works together, right? But I do also think that it's valuable to have models at a bunch of different levels of complexity so that you can see how these pieces work together in different ways and modeling hierarchy. It's wonderful.
Okay, thanks so much, everybody.